Hi everybody, welcome to my classroom. Today's topic is electric field. Here, I will explain electric field intensity, how to represent electric field, and finally, the properties of electric field. Let's start our class. Our topic is electric field and its properties. First, we want to discuss about the electric field. The concept electric field is introduced to explain the interaction between two charges. They may be similar or dissimilar. If they are similar, that is two positive charges or two negative charges, they repel each other. Otherwise, they are dissimilar or opposite charges, they experiences an attractive force. In this figure, the red one depicts positive and blue one is negative charge. So there exists an electric field around them. Here is the definition for electric field. In the region around the charged particle within which the other charges experiences the force of attraction or repulsion, and that region is called as electric field. So here we have two diagrams. First one is a positive charge and another one is a negative charge. In the first diagram, there is a positive charge and electric field exists around it and represented by imaginary lines with arrows pointing outward. The arrows represents direction of electric field, as you know. Then, in the second figure, there is a negative charge. Here the field lines are inward or towards the center of negative charge. Do you know why this happens? Why this the direction of field are different for positive or negative? The, this happens because we bring a test charge towards these charges. The positive charge always repels the test charge and the negative charge always attract the test charge. And hence, because of this reason, the electric field are moving outward for positive charge and field moving inward for the negative charge. So for positive charge, the field lines are outward direction and for negative charge, field lines are inward direction. Its symbol is capital E. It's a vector one and this represented by the imaginary lines. Its unit is Newton per coulomb or volt per meter. So next we want to discuss about the electric field intensity. Intensity means strength of electric field. The strength or intensity at any point is defined as the force acting on a positive charge placed at that point. So we have a figure. In this figure, the capital Q represents the source charge and small q is a test charge placed at a distance r from the source charge capital Q. And here F is the force, that is electric force, electrostatic force, and capital E is the electric field. Here, as the charge increases, the force also increases. Then F is directly proportional to Q. And F is also directly proportional to capital E, electric field intensity. And F is equal to a constant into QE, or K is equal to 1. We can rearrange the equation as F is equal to Q into E. And F is the electrostatic force acting on a test charge Q, and E is the electric field intensity around that source charge. Okay, so next, finally, we can solve the equation F is equal to QE or E is the electric field intensity equal to F by Q. So, what is electric field intensity? We can answer in a simple sentence. It's the ratio of force and unit charge, force per unit charge. Then, how much is the electric field intensity at any point? So we can write E is equal to F by Q. So then we can calculate how much electric field is acting at that point. Then in the second year also, we want to find some dimension formulas. So the dimension formula for electric field intensity is m raised to 1, L raised to 1, I raised to minus 1, and T raised to minus 3. You can calculate it using the dimension formula, that is F. For the dimension formula of F is m L T raised to minus 2. Then charge is what I raised to minus 1, T raised to minus 1. So we can got it. The next, the test charge. I think it's a new word for you. So test charge means what? So here a test charge is negligibly small. So in this diagram, plus Q denotes the source charge and Q0 denotes the test charge. Then our equation in the last we solved that E is equal to F by Q0. And actually that's not the correct or perfect equation for electric field. It is not the perfect equation, because if Q0 is greater, so the field of Q0 or field of test charge varies the field of source charge. So we want to consider the Q0 is very small, negligibly small. The test charge is considered to be vanishingly small because its presence should not affect the configuration of the charge and thus the electric field which is intended to be measured. So our equation E is equal to limit, that LT denotes limit delta Q tends to 0 F by delta Q0. Once again the same, if the test charge Q0 is large, the existing field of source will vanish or affected. That means it move away. So Q must be approximately equal to 0, but never it becomes 0. Okay. Then next, we want to find the mathematical, or we want to derive the mathematical expression for electric field intensity. First of all, we want to consider the diagram, and a brief description of the diagram is: consider a test charge, a source charge. Consider a charge Q, test charge at a distance R from the source charge capital Q. Once again, consider a charge Q, that's a test charge, small q, at a distance small r from a source charge capital Q. Then, using Coulomb's law, we can write the equation for electrostatic force acting between these two charges. F is equal to 1 by 4 pi epsilon 0 q divided by r square. In the original equation, we have 1 by 4 pi epsilon 0 q1 q2 by r square. Here, in place of q1 and q2, here q, capital Q and small q. Then if q is equal to 1 coulomb, that is test charge is very small and that must be equal to 1 coulomb, then we can rearrange the equation as F is equal to 1 by 4 pi epsilon 0 q by r square. Okay, then we can say this force per unit charge is called the electric field intensity. So that's the final equation. Capital E is equal to F by Q, or capital E is equal to 1 by 4 pi epsilon 0 Q by R square. Its unit is Newtons per Coulomb or volt per meter. So this is the derivation for, or mathematical expression for, electric field intensity at a point. Next, we want to discuss about two types of electric field. There are two types of electric field. First one is uniform electric field and the next is non-uniform electric field. So from this figure, we can understand very easily. For a uniform electric field, the field is constant at every point, but in non-uniform electric field, it is irregular. A charged particle experiences equal force at every point in uniform electric field. In non-uniform electric field, charged particle experiences different magnitude of force. Then uniform electric field are parallel to each other and equally spaced. Okay. Next, we want to represent the electric field lines. Representation of electric field lines. We have three cases. First one is a positive charge or Q greater than 0. Next is negative charge, that is Q less than 0. And next one is a dipole. A dipole means two poles. Here it is positive charge and a negative charge come closer to each other. That make a system. So first one is a positive and a negative charge. So they are separate figures. Positive charge is there, then negative charge is there. Only one difference is that for the positive charge, we should draw the arrow pointing outward. Then for the negative charge, should be pointing inward. And this is a dipole. Next condition is a dipole. So positive charge and a negative charge come closer to each other, and that make a system, and that is called as dipole. A positive charge and a negative charge separated by a small distance is called a dipole. Okay, that our next topic. So here once again the electric dipole, in electric dipole the electric field lines are originating from positive charge and ends at a negative charge. Okay, so that's the system. Next, our final topic is properties of electric field lines. For that, we are again considering this diagram for a dipole, and first property is that electric field lines start from positive charge and ends on negative charge. The electric field lines or electric lines of force originates from positive charge and ends on the negative charge. That's the first one. Second one is electric field lines never intersect each other. Two lines of forces never intersect each other. That means if they cut each other or join each other at the point of intersection, there will be two tangents. This indicates that there will be two directions of electric field at the same point, which is impossible. So, two lines of force never intersect each other. And next one is the field is strong when the lines are close together, and it is weak when the field lines move apart each other. Okay, from that figure, it's very clear. Near to that positive and negative charge, number of lines are there. So field strength is very greater than that of the space away from that. So next property is the number of field lines are directly proportional to the magnitude of charge. Once again, number of field lines are directly proportional to the magnitude of charge. If we have 1 coulomb charge, less number of field lines are there. We have 50 coulomb, we have more number of field lines are there. So the field lines are perpendicular to surface of charge. The field lines are always perpendicular to the surface of charge. So these are the properties of some of the important properties of electric field lines. So that's our topic. First we discussed about electric field, then next electric field intensity, and then how to represent electric field, then how we can derive some equation for electric field intensity, then finally the properties of electric field intensity. Okay, thank you.